Okay, so what we're doing today is calculating the equilibrium constant. So last lesson we did a bit on um, finding the K expression, the K equation, um, and so we're going to start using that with some numbers, basically. Now our syllabus outcome is the same one. Deduce the equilibrium expression for homogeneous reactions occurring in solution. So revision. If you haven't done the revision questions, do them now. Pause the video, and then come back for the answers. So the equilibrium constant, it's a number that describes where the concentration of reagents at equilibrium lies. For the equilibrium reaction, AA plus BB is an equilibrium of CC plus DD. The equilibrium constant is given by the KQ equation, concentration of C to the power of the stoichiometric ratio C, concentration of D to the power of the stoichiometric ratio D over concentration of A to the stoichiometric ratio A and times the concentration of B to the power of the stoichiometric ratio B. Remember, with products over reactants equals K. So the equilibrium constant. Um, the equilibrium constant is a numerical value that is always greater than zero. Okay, if you've gotten a negative for your K equation, then you've done something wrong. Okay, I'll just say that straight off the bat. All concentrations should be positive. All the powers should be um, 1 or above and an integer value. Um, and so the number will always be greater than 0. Okay, it can vary quite drastically, from like 10 to the 30 down to 10 to the negative 50. But it will always be above 0. Now, the value shows where the equilibrium lies in a chemical system. Now, what we mean by that, if the value is less than 1, the equilibrium favors the reactants. Now, if you remember our K equation, so K is concentration of products over concentration of reactants. Effectively, like this is just a blatant simplification. If the value is less than 1, it means that the reactants number is bigger than the products number. Okay, so remember, for a fraction to be less than 1, the denominator needs to be bigger than the numerator. Now, if the value is greater than 1, it's the other way around. The equilibrium is favoring the products. It means there's more products than there are reactants. And again, in terms of fractions, for a number to be greater than 1, the numerator needs to be bigger than the denominator. Okay? So, it's calculated by substituting in the values of the concentration of reagents at equilibrium. Okay? So basically, in a question you'll be given, it'll say, at equilibrium, the concentrations are blah blah. You substitute those values into your KEQ equation. So here's an example straight off the bat. For the equation N2 plus O2 is in equilibrium with 2NO. Determine the equilibrium constant if the concentration of reagents at equilibrium are N2. The concentration of nitrogen is 0.5 moles per liter. Concentration of oxygen is 0.5 moles per liter, and the concentration of nitrogen oxide is 2 moles per liter. So what do? The very first thing that we have to do is find the KEQ equation. Okay, find our K expression. So products over reactants equals K. So it's going to be products for NO, and it'll be squared. Reactants are oxygen and nitrogen, and they're both stoichiometric ratio of 1, so they've got just the power of 1. So our KEQ equation is that one. So NO squared over N2 times O2. Now, once we've got the K equation, we substitute in the values that we had. So that's our K equation. I believe the concentration of NO was 2, the others was 0.5 from memory. Okay, and so we just substitute that in, and we get 16. And so that is the value of KEQ for this reaction at this temperature. Basically, what that shows is that it favors the products, okay, because it's a number greater than 1. So there's more products than there are reactants. And in this case, it's about 16 times the number of products to reactants. So that's not always going to necessarily be the answer. But yeah, in this case, it's about 16 times. So let's try another one. So for the equation, N2 plus 3H2 is in equilibrium with 2 ammonia, our old friend the Haber process. Determine the equilibrium constant if the concentration of reagents at equilibrium are 0.1, 0.4, and 0.9. Okay, so first things first, we need to get the K equation. So we did do this one last lesson, but same as always, for this equation, so nitrogen plus 3 hydrogen in equilibrium with 2 NH3, it's going to be products over reactants, so concentration of ammonia squared over concentration of hydrogen cubed times the concentration of nitrogen. So it gives us this. Okay, so that's our K equation for this reaction. We then substitute in the values that we were given. So with our K equation, take the numbers from the question, put them in. So 0.9 squared over 0.4 times 0.1 cubed. That gives us 2025. So in this case, it is very, it's favoring the reactants quite a bit. Okay, so it's pushing very well towards those products. For the equation, 2SO2 plus O2 gives us, is in equilibrium with 2 sulfur trioxides. Determine the value of KEQ if those concentrations. So sulfur dioxide 0.003, O2 is 0.06, sulfur trioxide is 4.3. So write the K equation. So again, we've got products over reactants equals K, so it's going to be concentration of SO3 squared over the concentration of oxygen times the concentration of sulfur dioxide squared. So I'm going to get this. Okay. We then take that K equation, substitute in the values that we had. Okay. So it gives us 4.3 squared over 0.003 squared times 0.06, which gives us a huge number, 3.42 times 10 to the 7. Basically what this is saying, and we can kind of see this from the concentrations that were given to us, but this equilibrium is definitely favoring the sulfur trioxide side, so the products. We can see that the products have a concentration of 4.3. One of the reactants only has a concentration of 0.003. So that's why we've got such a big KEQ value. Okay, so summary. So the equilibrium constant's a numerical value that shows where the equilibrium lies in a chemical system. It's calculated by substituting in concentrations of all the reagents at equilibrium. If the value is less than 1, equilibrium favors the reactants. If the value is greater than 1, the equilibrium favors the products. Okay. So having said that, please go ahead and do the exercises for this lesson. And yeah, we'll move on to looking at what we call the reaction quotient next. And so that's all for today.